Okay, we're going to get back to section 5.5 and talk more about substitution for integration. I mentioned the importance of knowing a U substitution going into Calc 2. I feel like that is super important for a Calc 1 student to be good at a U substitution while moving on to Calc 2. That's one of the first things I tell my Calc 2 students is you have to be good with that stuff, just because we use it so much. But of course, like anything else, it's the more you practice, the better you get type thing. So let's just take a look at some more examples here. This was the last one I did in the last video there. And okay, suppose that we want to integrate the function 1 over 4x minus 1 dx. Okay, well, I'd want to use a U substitution on this. And by the way, you'd want to consider a U substitution whenever you don't see how to get to the antiderivative pretty much immediately. Okay, and some of these, there'll be some algebra, and then you go to the antiderivative. But if you don't see that, probably the next thing that you're wanting to consider is a U substitution. We're going to let U be 4x minus 1, and du would be 4dx. Okay, now remember, the idea with a U substitution is to see a function in the integrand whose derivative is also in the integrand. If I divide both sides by 4, dx, which is in the numerator, can be replaced with 1/4 du. Okay, and 1/4 is a constant that can come out of my new integral involving u. And so inside my new integral, I'm going to have 1 over u du. Okay, and of course, we're trying to make the integral easier than it was previously. And everything about the new integral has to be in terms of the new variable u. Okay, you never want to mix u and x. If that ever happens, you don't have the correct U substitution. Okay, or possibly a U substitution didn't work. Okay, and so there is more to know when it comes to integrals. The antiderivative of 1 over u is the ln of the absolute value of u. U is 4x minus 1, so my answer would be 1/4 times the ln of the absolute value of 4x minus 1 plus a constant. Be sure to include absolute value bars in your answer. If you don't have them, it is a wrong answer, because we know we can't take ln of a negative. Okay, and x can be anything, of course, if x is anything, you can sometimes have negative numbers in this expression 4x minus 1. And also, I've mentioned several times, make sure that you include the plus c at the end there. Okay, how about this one? The integral for 1 over x times the ln of x dx. Well, if I were to let u be the ln of x, I know the derivative of the ln of x is 1 over x, and there's a 1 over x dx in the integral. So when I write my new integral here, I'm going to have the integral for 1 over x dx is du, and then ln x is u, so 1 over u du would be inside the integral. Antiderivative of 1 over u is the ln of the absolute value of u. Replace u with ln x, and so we've got the ln of the absolute value of the ln of x plus c. Again, make sure that you include the absolute value bars there in your answer. Okay, here's one. Suppose that we want to know the antiderivative of tangent x. Well, I know the derivative of tangent x, that's secant squared x, right? That has nothing to do with what we're doing though. Okay, don't confuse derivatives with antiderivatives. Some students will do that. Okay, especially at this point, don't do that. Okay, now we want to know the antiderivative of tangent x. Okay, so what function has a derivative that is tangent x? Well, tangent x is the same as sine x over cosine x, and I'd want to think about it in that way, because then I can consider using a U substitution here. Now, I mentioned in the previous video, sometimes a U substitution involves some guessing and checking. Okay, like if I were to let u be sine x, then du would be cosine x dx. Now I don't have a cosine x dx. Dx is always in the numerator, okay, of a fraction, if you have a fraction in the integrand. So I'd want to let u be cosine x. If u is cosine x, du would be negative sine x dx, and I've got a sine x dx in the numerator there. The negative can come out of my new integral involving u. So my new integral would be negative the integral for 1 over u du, and that is equal to negative the ln of the absolute value of u plus c. Replace u is cosine x. And if you were to take this a step further, your book would probably do this using some laws of logarithms. This negative 1 can be pulled inside the logarithm as a power of the inner part. Be careful how you write that though, okay? Cosine of x to the negative 1 power is not the same as cosine inverse of x. Okay, cosine of x to the negative 1 power, that's the same as 1 over cosine of x, which is by definition how we describe secant x. All right, so if you were to rewrite the answer without that negative multiplier there, ln of the absolute value of secant x plus c would be the answer. Okay, now another thing to mention is that along the way here, as we're learning about integrals, there are some integrals that you will want to have memorized. Okay, just because they'll come up over and over and over again. And I mentioned there is more to know with integration. You'll be hit real hard with integration techniques in Calc 2. That's there's Chapter 7 is all about integration techniques, and so. But actually, if you were to look in the book, at the very first page of Chapter 7 is a list of integrals that your book wants you to know at this point, because these integrals come up a lot and they're just worth knowing. This would be one of them. Okay, know that the antiderivative of tangent x is the ln of the absolute value of secant x. Okay, I'll mention some other ones that are worth memorizing. Of course, we've already seen some basic ones. Like the reverse power rule. So the antiderivative of x to the n would be x to the n plus 1 over n plus 1. Antiderivative of e to the x is itself e to the x. The antiderivative of cosine x would be sine x. Antiderivative of sine x would be negative cosine x. Things like that you'd want to make sure that you know. And of course, we already know some of that because of what we already know with derivatives. Sometimes integration involves some algebra and creativity, okay? And like in a problem here, okay, if I were to let u be x squared plus 1, which is the only thing that I'd want to consider in a u substitution for this problem, then that's not going to work. Because if u is x squared plus 1, du would be 2x dx, and I don't have a 2x dx in the numerator, right? I've got an x squared plus x plus 1 dx. And so at this point, a u substitution is not going to work. Well, let's go ahead and divide this out. Okay, if we go back to algebra and long division for polynomials, I've got a side calculation where I've done that. X squared plus 1 is going to go outside the division bar. X squared plus x plus 1 will go underneath it, and I'll begin dividing. So I know that 1 times x squared plus 1 is x squared plus 1. I want those leading terms to match, because when I subtract these expressions, x squared minus x squared is 0. The leading term is gone. X minus 0 is x, and then 1 minus 1 is 0. Okay. I'll have leftover information. X is the remainder, okay, but the complete leftover would be a fraction that you'd be adding to the quotient. The fraction that we'll want would be x over x squared plus 1. Okay, so when I actually divide this out, as I've done, I get 1 plus x over x squared plus 1. Well, I know the antiderivative of 1 is x, and of course I can split this integral into two integrals. I've done that. And the first one, like I said, is x. I can get that right away. The second one, okay, now I can use a u substitution. If I were to let u be x squared plus 1, du would be 2x dx. I've got an x dx in the numerator. A 1/2 can come out of my new integral involving u. And so 1/2 the integral for 1 over u du would be my new integral here. Antiderivative of 1 over u is the ln of the absolute value of u. U is x squared plus 1. So I'm looking at x plus 1/2 times ln of the absolute value of x plus 1 plus a constant. Now, by the way, this would be a rare time where if I didn't write the absolute value bars, that would be okay for this problem. X squared plus 1 will never be a negative. Now, there's no problem with having them. Okay, in fact, I would encourage you to have them just to make it routine, although sometimes you actually don't need them, but that's rare. Okay, 1/2 can be pulled up inside the logarithm there, and x squared plus 1 to the 1/2 power would be the same as the square root of x squared plus 1. And some of these problems, your book will, take it a step further, and they'll use like the laws of logarithms, just to simplify a bit further. Okay, and so here'd be my answer. Now, one of the things to mention about integration is integration is not as straightforward as differentiation. What I mean by that is when you're given a function and you want to calculate the derivative, you should always have a plan, at least about how to begin the problem. Okay, like you should know right away at this point, okay, I'm going to need a product rule, a quotient rule, a chain rule, or I'm going to do things with the trig functions or exponentials, or I got a logarithmic differentiation, or things with inverses. Okay, like those are all very clear rules that we've and they're all stated in chapter 3. And we've done several things with derivatives, right? Now, antiderivatives are different. Okay, it's not as clear cut. Sometimes we need to simplify the integrand. Sometimes we need to use the u substitution. Sometimes we need a little creativity. Okay, and sometimes we need to use methods that you guys haven't even seen yet, and you'll see in Calc 2. Okay, it just depends on the function that you're integrating there. Also, it is worth saying that some functions are said to have don't have what's called an elementary antiderivative. Okay, now what I mean by that is that it is impossible to find the antiderivative using methods that we know. Okay, you'll learn a lot about that in Calc 2, actually, in Chapter 7. And here's some examples. The integral doesn't have to be overly complicated for it to be impossible. All 6 of these integrals are ones that you would see again in Calc 2, and all 6 of them are not possible to integrate using methods that we know. Or we would say that they don't have an elementary antiderivative. Okay, these are not complicated functions that are inside the integral. Okay, but they are impossible. Now that adds to the difficulty of integration when you compare it to differentiation. Okay, integration is way more difficult than derivatives. All right, and so there are some rules that we can establish when it comes to integrals, but it really just depends. I've stated that it just depends on the function and how the problem needs to be done. So here's another example. Okay, suppose that we want to integrate secant x. Okay, well, now here's where the creativity part comes in. So there's a sneaky little trick that I would not expect anybody to ever see unless you've read the book, so I'm just going to tell you what it is. You're going to think about secant x as secant x over 1, and you're going to multiply the top and the bottom by secant x plus tangent x. That's an obvious move, right? Not really. I'm kidding around. But the reason why we would do this is because we're setting ourselves up for a u substitution. Okay, if I distribute secant x into these two terms, and then I'm going to let u be secant x plus tangent x. Du would be Okay, the derivative of secant x is secant x tangent x, that's what I got there, plus the derivative of tan x is secant squared x dx. Well, that's exactly what I have in the numerator. Right, so u substitution is going to work out great here at this point. I'll get the integral for 1 over u du, which would be the ln of the absolute value of u, plus c. U is secant x plus tangent x, so I've replaced that and given my answer in terms of x. And yeah, so that's kind of what I was talking about earlier. You know, sometimes you need a little creativity with it, okay? That's just part of what you get with integration. And again, I'll re-emphasize that, you know, it's like anything else. The more you practice, the better you get. Okay, and the idea is that we want to establish the fundamentals when it comes to integration. Okay, and we want to build on the fundamentals. Okay, we got to start somewhere. But there's a whole lot more to know about integration, and like I said, you guys are just, you know, touching the surface of this, and you'll be talking a lot about integration in Calc 2. Let's take a look at this one next. Here's another one where we're going to need some creativity. Suppose that we want to integrate x times the square root of x plus 2 dx. Okay, well, if I were to, by the way, there's no algebraic simplification that I can do here in order to just go right to the antiderivative. Of course, I can't split this radical, right? Some students would make that mistake. Don't do that. Now, if I were to let u be x plus 2, then du would be dx. Now, what about this x out here? Well, if u is equal to x plus 2, and you subtract 2 from both sides, x would be u minus 2. So I'll be able to replace x with an expression entirely in terms of u. Okay? Du is dx, like I said, so I've replaced that. X is u minus 2, and then the square root of x plus 2, that'd be the square root of u. Okay, now that allows me, this new form allows me to distribute the square root of u into each of the two terms there inside the parentheses, and I've done that on the next line. And I'm using fractional exponents. That allows me to use the reverse power rule to get the antiderivative here in terms of u. Okay, it's going to be u to the 5 halves divided by 5 halves, same as multiplying by 2/5, minus 2 times u to the 3 halves times 2/3, or that'd be a minus 4/3 u to the 3 halves, plus a constant. Okay, and then of course the last thing, replace u with x plus 2 so that your answer is in terms of x. Now the point of this is to say when you are trying to set up a u substitution and it doesn't initially work, don't give up on it. Okay, sometimes you might need some algebra within the substitution equation to be able to replace everything in the integrand so that it's in terms of u, like we see here. Okay. Why don't we take a look at one more? So we want to integrate e to the 2x divided by e to the x plus 1 dx. Well, there's no algebraic simplification that I can do to begin something like this. I'm starting with a u substitution. I'm going to let u be e to the x plus 1. Now, if u is e to the x plus 1, du would be e to the x dx. E to the 2x, that's the same as e to the x times e to the x. So what about this extra e to the x that's going to be in the numerator? Well, I can replace that, because if u is e to the x plus 1 and you subtract 1 from both sides, that extra e to the x is going to be replaced with u minus 1. All right, so check it out. Here's my new integral. In the denominator, I've got u. Now, e to the 2x, that's the same as e to the x times e to the x. E to the x dx is being replaced with du. Now, that extra e to the x is being replaced with u minus 1. So everything is going to be working out here where I get my new integral in terms of u. I can then split this into two fractions. I've done that. 1 minus 1 over u. Then I can go to the antiderivative here in terms of u. It's going to be u minus the ln of the absolute value of u plus c. U is e to the x plus 1. Okay, and so I've replaced that. And A couple things. So first of all, here's another situation where I don't need absolute value bars. There's no problem with having them, but you actually don't need them if you don't want them. Now, an answer that you might find in the book is, for a problem like this, they might give the answer as e to the x minus the ln of e to the x plus 1 plus c. Now hold up, what happened to the plus 1? Well, a constant plus 1 is a constant. Okay, so we don't really care what that constant is at the end, just it's a constant. So both answers are acceptable. Okay, it's just this is probably the answer that you'd see in the book where, hey, we don't care what that constant is at the end. And so sometimes, we'll have to combine the constants all as one constant in the end when we give our answer. Okay, I'm fine with keeping the answer in this form, though, if you want.